I'm Manav. My project for Math 2850 is on the SIR model for infectious diseases. We can start by talking a little bit about the basic SIR model. The SIR model is the most basic compartmental model of an infectious disease, and it splits the population into three distinct subgroups. S is the proportion of the population that is susceptible to the disease but has not contracted it. I is a proportion of the population that is actively infected with the disease, and R is the proportion of the population that has had the disease and they've recovered from it. These three subgroups make up the entirety of the population, so S plus I plus R always equals 1. The SIR model makes a few major assumptions. The first is that the overall population does not change, so DDT of S plus I plus R is always 0. The second is once a person has recovered, they cannot become infected again. So movement always goes from the S subgroup to the I subgroup and then finally to the R subgroup. The third is the rate of transmission of the disease is proportional to the number of encounters between susceptible and infected people. And finally, the growth rate of the recovered population is proportional to the proportion of infected people. Let's consider the third and fourth assumptions to determine some rate equations and differentials. So we had that the rate of transmission of disease is proportional to the number of encounters between susceptible and infected people. So when we're talking about the rate of transmission of the disease, we're really considering movement from the S subpopulation to the I subpopulation. So that's why here we're defining ds dt. And so we need to look at the encounters between susceptible and infected people, and that's why we multiply those proportions together. We have I times S in there. And we use beta as a scaling constant, and that's the rate of infection. And it's negative because as people are infected, they're leaving that subgroup. Okay, and then our fourth assumption was that the growth rate of the recovered population is proportional to the proportion of infected people. So here we're describing movement from the I group to the R group. And so really what we're describing is the growth rate of the R group. And that's just equal to the number of infected people times the scaling constant. Here we're using gamma as the recovery rate. Because we make the assumption that the population is always constant, so DDT of S plus I plus R is 0, we see that the rate of change of the infected population is equal to negative the rate of change of the susceptible population minus the rate of change of the recovered population. So we determine that di dt is beta IS minus gamma I. So really what we're seeing here is the rate of people leaving the susceptible population and joining the infected population minus the rate of people leaving the infected population and joining the recovered population. Based on that same assumption, we can fully characterize the population with just two subgroups. Here we're just using S and I because we know that the third subgroup is just 1 minus the sum of the other two. Okay, so given that information, let's take a look at an example problem and see how we can apply concepts we learned in class. So consider a disease with an infection rate of 0.375 and a recovery rate of 0.125. Determine a model for the proportion of infected people in a fixed population if 95% of the population is originally susceptible and 5% is originally infected. So given the rates we're given in the first sentence here, we determine that beta is 0.375 and gamma is 0.125 for our calculations. We also have that S0 is 0.95 and I0 is 0.05. So given the equations for the rates of change of S, I, and R that we determined before, a really good way to model this disease in this case is to use Euler's method because we're given some initial values and we're giving the values of all of our scaling constants. So if we use Euler's method, we find that these are how we find the next iteration of S, I, and R. And so we can create a graph of this model. So in recent years, during the pandemic especially, we heard a lot about flattening the curve to combat the COVID-19 pandemic. And the curve that we're referring to there is the curve of the infected proportion, that dashed line in the middle right there. So our goal was to flatten that curve. I made this graph using matplotlib in Python. So if you're interested and you want to play around with some numbers, I've linked my code in the description to this video. In summary, we talked about the basics of the SIR model for infectious diseases, defined the relations between the subpopulation proportions, and looked at an example. Beyond this is analyzing fixed points in the model, explorations of vaccine efficacy and herd immunity, and removing some assumptions with the SIRF model. Thank you for listening.